Let us do an energy and entropy analysis of an open steady device, a turbine in this case. I've picked up a problem from chapter 4, and since this is a problem about the PG model, we'll replace steam with, let's say, air. At the end, we can come back and see what answer we get if steam is treated as a perfect gas. So let's see what is given in this problem. Air enters the turbine. The inlet conditions are given. We'll call it, say, state 1. And mass flow rate is given. An exit pressure is given. So at state 2, which will be our ideal exit state, and state 3 will be an actual exit state. So the pressure, of course, will be 200 kPa, whether the turbine is ideal or an actual turbine. Okay, so let's begin. First thing first, we draw a TS diagram showing the ideal and the actual turbine. Recall that the constant pressure lines looks like this. So this is the pressure line of 4 MPa for a perfect gas. Let's say this is state 1. So this is the 4000 kPa line, and the air expands to 200 kPa. So this will be a 200 kPa line, and in an isentropic case it will come down vertically, and we know that in an actual turbine the exit entropy will be slightly higher. Okay, so state 1, let's write down everything that is known. Pressure, I'm converting that to kilopascals. Temperature, instead of Celsius, let's go straight to Kelvin. And mass flow rate is supplied. Okay, to find state 2, we recognize that entropy remains constant. And what formula should we use for an isentropic case? So state 2, let's write down again. We know pressure. And we know the entropy at 2 is entropy at 1. So for PG model, the formula we open test, and if you go to the property tables, I'm showing that table one more time. If you go to table J, if you go down to table J, is the formula sheet. I'm assuming you already have a printout of that. Go all the way to the bottom of this and you will find all the different material model, the equations, all the models separated. So this is our PG model. And in the PG model, you can see equation 11 is the isentropic. If entropy remains constant, use one of this convenient relationship. So look, if you know the temperature ratio, pressure ratio can be found, and vice versa. So we pick up this formula and go back. We recognize you can write, again, just to remind you, we have state 1 here, state 2 here. So the higher temperature T1 over T2 will be P1 over P2 to the K minus 1 over K. So that gives us T2 equals, we want to find T2 equals T1, which is 873 divided by what is P1? If you recall, this is 4000 and this is 200. So their ratio is what? 20 to the, and K value is well known. So it's 873 divided by 20 to the 0.4 over 1.4. And let's take advantage of a test calc to even do this calculation. So we go to test calc and we follow the system analysis open steady system branch, generic branch, because This is not about a specific chapter. So we go to a single flow generic device. Single flow means there is only one inlet and one exit, and our model in this case is the PG model. We click on this tab to get the test calc started. Now I just wanted to show you how we can use this as a simple calculator. For that, we go to the I/O panel, and to evaluate the expression, we can just write, say, equal. So I'm writing this at the bottom of the screen here, equal. We want to evaluate, remember, 873 divided by 20 to the power 0.4 divided by 1.4, and I have another parenthesis, so it's 371 Kelvin. If you want to verify that answer, we go back to test calc, this time to the state panel, select air, pressure is 4000 kPa, temperature I believe was given to us to be 873 Kelvin, right? And mass flow rate was 5 kg per second, so that's all about state 1. For state 2, we had 200 kPa and entropy remains constant. P equals P, S1 equals S2. Mass flow rate doesn't change. And we calculated the temperature, so it's matched with what we calculated. And as you can see, we can do a TS diagram to make sure the entropies are vertically aligned. If you do the constant pressure lines, that's how they look on the TS diagram. And just to remind you, if you recall from our auto cycle problem solutions, constant pressure lines, constant volume lines are steeper than constant pressure line in a perfect gas, for a perfect gas. So again, you can see evidence of that here. Okay, now let's get back to the problem. So we found state 1 temperature, state 1 is given, state 2 we've just calculated. So therefore, we can do a energy analysis for the turbine. The EDT m dot J1 minus m dot J2 plus Q dot, right? So steady state, 0 equal, and we are just writing J equals H, and W dot turbine is our ideal turbine. So let me write down ideal here to remind us that this is isentropic turbine. So therefore, W dot T ideal, and if we use the formula for H1 minus HT, and T1 was 873 and T2 was 370. Is that what he calculated? Yes, 371. Once we calculate this, it turns out to be 2521 kilowatts. So that's the maximum power out of the turbine. Let's go and verify this. We already calculated the two states. Go to the device panel. We load state 1 and we load state 2 as inlet and exit state. Heat transfer equals 0. And it is 2521, exactly what we calculated. So we found the turbine power when the turbine is isentropic, that is its ideal turbine. Well, let's do the second part of the problem, that if the exit temperature, what was the second part? If the exit temperature is 220 degrees Celsius, determine the isentropic efficiency. So as you can see, if the exit temperature is 220 Celsius, which is state 3. So for state 3 now we know the exit temperature let's say 273. So therefore, the actual turbine output m dot h1 minus h3. Recall, m dot h1 is the energy carried by the flow into the turbine, and m dot h3 is the energy that is leaving the turbine in an actual turbine. And so that becomes m dot cp t1 minus t3 for the PG model. Again, from handout J you can figure that out. It's written in the under the PG model, these formulas. Substituting 5 kg, let's take a value of cp to be this 873 and 493, and the answer turns out to be 233 kilowatt. Let's go verify this. So to calculate state 3, we know the pressure remains the same as P2, and the temperature is given 220 degree Celsius. Same mass passes through the exit as the inlet. So 493 in Kelvin, so it's correct. Let's go to the device panel, select a different device, device B, select state 1 as the inlet and state 3 as the exit. Again, it's adiabatic turbine, and oops, we must have made a mistake somewhere. State 1 should be the inlet, sorry. Do I calculate again? So we still have an error. Let's go and check this. So let's do a TS diagram. Okay, so let's go and check the value we got here, 1906, with the value we got in our manual calculations. As a matter of fact, I just checked these numbers, and it is indeed 1906 kilowatt. So now that we have the actual power and the ideal power, the thermal efficiency we can easily obtain. I'm sorry, the turbine efficiency or the isentropic efficiency is obtained as turbine efficiency W dot turbine. Now, which one goes on top, the actual or the ideal? Obviously, the ideal power is much higher than the actual power, and that's how the isentropic efficiency is defined. So we divide the two numbers. One is 1906 and the other is 2521. And that's approximately equal to 0.75 or 75%. So what would be an actual entropy analysis of the turbine look like? Again, recall that in this turbine, state 1 is the inlet, and we have 2 for the ideal turbine and 3 for the actual turbine. Well, the entropy equation is quite simple, and let's do it for the actual turbine, because for the ideal turbine it's really quite simple. So in the actual turbine, as in the ideal turbine, steady state, this term goes to 0, and adiabatic, so there is no difference here, except in an actual turbine there could be entropy generation because friction is allowed inside. So what this equation tells us is that the entropy that lives with the flow at the exit of the turbine equals the entropy that enters plus the entropy that gets generated because of irreversibilities, because of friction inside the turbine. Suppose we have a question that determine entropy generated inside the turbine. So that is, to answer this question, the answer would be simply this expression which can be evaluated if we use the PG model, because we know how entropy difference formula looks like, which is quite simple. For the PG model, it is Cp ln temperature ratio minus R ln pressure ratio. Again, if you go to the handout J, the table J, you will find this formula under the PG model group. So now that we have all the numbers and the formula, we can easily find the entropy that is generated. T3, I believe, was 493 we calculated, and T1 was given to us 873. Value for R for air, and the pressure dropped to 200 from 4000 kPa. So temperature dropped in the turbine, so therefore we know the temperature drop means entropy decreases. However, the pressure drop means entropy increases. So in combination, the pressure drops makes entropy increase more than the temperature drops reduces, resulting in, if you calculate, this is about 1.43 kilowatt per Kelvin. So this is the measure of how much friction is there in an actual turbine. Of course, in an ideal turbine, you will find it to be zero by definition. That's why entropy remains constant. That is the reason an ideal turbine is isentropic. Let's go make sure this is what we get in our device panel. If you go to device B, that's the actual turbine, and see the entropy generation is given here. The value of TB is irrelevant because heat transfer is zero anyway. Now that we have a complete test solution, let's explore some of the ramification of the assumptions we made. Let's first try to see the effect of neglecting KE and PE, which we routinely do. But let's establish how important kinetic and potential energies are. So let's first write down what was the ideal turbine output. Let's go back to the screen. 2521, that was the solution we got. And now we'll allow potential energy to be significant and see how much the answer would change had we not neglected potential energy. So we'll make up a scenario here. At stage 1, we'll say, okay, at the inlet, the turbine height was 2 meters, and we'll leave the exit as 0. So we'll calculate the state with this updated information. And at stage 2, turbine height is 0. In other words, we have now a potential energy difference between inlet and exit. To update all the calculations, simply we click Super Calculate. So the turbine power for the ideal device is device A has been updated. It is 2521.2. So if we include kinetic energy, potential energy, this become, so PE has almost no impact. Okay, let's try now the potential energy. Again, we are going to go and we'll get rid of the, first we get rid of the potential energy. We set it back to 0, the elevation Z. And this time the inlet velocity, let's pick some typical number. At a turbine inlet, let's say the velocity is 10 meters per second. And notice when you calculate, enter a velocity other than 0, the turbine inlet area is calculated. That's an interesting number by itself. We'll come back to that in a second. So first, let's look at the impact of kinetic energy. At the exit state, suppose it's given the exit velocity is 20 meters per second, it doubled. So if we set them to 0, we already got an answer. And now suppose you are calculating including kinetic energy. Obviously, if you in your manual solution, the turbine power will be m dot J1 minus J2, which will include kinetic energy now instead of H1 minus H2. So if you do a super calculate, let's find out what is the result. 2520.3 again. So it's like it's barely any difference at all. So this result become, oops. This is the effective kinetic energy, and this is the effective potential energy. As you can see, it's almost negligible. But look at the turbine inlet and exit area that we calculated. What is A1 and A2? Now that we have put some reasonable velocity of the steam of the air entering and exiting the turbines, the inlet area was let's say 0.03 meter square, and the exit area is 0.13. So as you can see, steam air expands through the turbine, so the exit area has to be way bigger than inlet area. That's why when you see a drawing of turbine, we generally draw it like this, just to indicate that the exit area has increased. Finally, a solution such as this can be stored using test codes. Let me just show you how it works. Okay, we'll set back our numbers to the original solution, which is we neglected the kinetic energy and potential energy. But note that when you set velocity to 0, the area calculated will be an arbitrarily huge number, like infinity, because the mass flow rate 5 kg per second with 0 velocity, the solution will become area to be infinity. But it doesn't change anything about the energy or entropy balance. So we are fine when you neglect kinetic energy by setting velocity to 0. Going back, if you click the super calculate on a solution, you'll notice that it switches you to the I/O panel, and in the I/O panel, a detailed calculation results are displayed. If you print it out, it's almost like all the results you need to know about this turbine problem. But embedded in this, you'll find a test code, a bunch of macros or a bunch of statements telling what is known about the problem. So you simply copy this test code, Control C, and let's say we come and paste it here for our, oops, it's a too big a font. Let me see if I can change the font here. Okay, so here we go. So that's all. So if we store it somewhere, later we can simply copy and paste the code and regenerate the solution. Just one more idea. Notice that we have solved this turbine problem for air. Suppose this problem involves H2O. How will the result change? So suppose we select H2O. Yes, H2O can be treated as perfect gas. Suppose H2O is superheated. And in that case, perfect gas assumption is not that bad. But let's calculate what happens to the turbine. All we do is to select H2O and super calculate. Now, steam is now being treated as a perfect gas, and all the solutions produced. I want to write those down because in a separate problem, we are going to handle steam as with this appropriate model, which is PC or phase change model, and see the answer, the more accurate answer compared to this PG model answer. So in this, if we use H2O, we get an ideal turbine output of 4264. 4264. So let me write that down. If we use for when we use the PG model, how much was it? 4263.69. And actual work is 3548.6. Both are way more than what the steam, what the air turbine produces under the same conditions. So anyway, so we'll keep this in the background, and when we solve the problem with a PC model, we like to see what are the more accurate answers.